G'day guys. Going to do a bit of a discussion about pulse induction coils. I've gone out into the garage and I found some coils I made a long time ago. Actually, I've been making coils, good, 10, 15, I don't know, about 20 years or so. And some of these early coils for pulse induction detectors, what we ended up doing is we didn't have, I better put it around here, move that around. I've got one of the ones I made. We used to use the old commercial coil housings when we made these. Like you could look at this. That's an old Minelab 18-inch coil. I think this came off I think it came out with the SD 2200. Serial number 2200. Isn't that interesting? Or is that uncanny? Can you see it in the middle there? That's a serial number, 2200, but I think it came off a SD 2200 detector. Might have been a 21, long time ago. Can't be accurate going back that far into the past. But anyway, I'll give you an idea on these coils. This is one I made. You can tell that it's so thick that it wouldn't have, it doesn't actually fit into the housing properly. But I just put some pneumatic tape around it when I used it. Now, I'll tell you a little story about these coils when I was making them. We had these coils tested independently, and these people are industry people. They are in the metal detector business, and they got a test site, and they used these coils, and they said it was the best coil they ever used. It was, from memory, it was very quiet, and they go very, very deep. And they actually give a better signal than some of the other similar sized coils. And there is reasons for it. Now, these coils, I've got the meter here, if you can see it. And I'll just go across the carbon on this, about 1 centimetre, roughly. Okay. So 120 ohms odd. We used to make them 80 ohms for memory per centimetre. You go out to 1 inch and 157. But anywhere on the coil, if I go, from here to here, right across the coil, 494. But in different parts of the segment, it will change. There's a reason for this, and I'll explain it. This is a very, very low noise coil. And what it is, in the shield, this graphite type carbon based paint, here is just masking tape. Stuff painter's tape, I suppose you call it. And where there's a groove in it, I've removed the carbon here and here. And the reason why I remove the carbon is that I don't get a fully conductive plate all just joined together as a large object. And there's a reason for that. And you can see the different height in the tape here. What happens here? I'll give you an example on this segment. This is how you make a really, really good coil. This is actually connected. The tape is painted into this. So that's a hard connection from the tape. But here, the tape is not painted onto this side. It's an overlap, and the carbon is underneath on this, but it doesn't touch that. So having the overlap acts as a shield. You still can't get any interaction through the overlap. It won't happen. But if that wasn't there and it was open, you'd have an interaction with the ground to the coil, and every time you put this near the ground, it would signal off. That's one of the problems with these coils, or any coil for a pulse induction detector, that sometimes you bang them and they sound off. And that, in most cases, is this shielding material, whatever it may be, it moves in relation to the coil winding, which is in here. Now, like I say, these are very early coils. They're a bit rough, but boy, did they work well. And on the day they were tested, well, they've been tested a few times, but on the particular day with third parties testing, I remember it was 37 degrees Celsius. It was very hot. And a lot of the ground and the coil combination, and I've never done the actual measurements on it, but a lot of the standard commercial coils get very noisy. This one didn't. It did not get noisy. So you can work out your own mechanisms for that. So there's a channel in here, the wire's running here, it's got tape over it, it is totally shielded. And again here, on this side, it's a 4-quadrant break overlap shielding system. Again, it works beautifully as a shield. And the other important part as well is where the windings are, that the tape, like this is just the old masking painter's tape here as well. But when you paint it, it goes hard, it won't move. So I can see it, I'm pushing on it, and I can move it about 0.5 millimeter, but that would still sound off if you bang the coil. But in normal operation, it's not going to move. Normally, you'd probably put some type of aerated foam in there to hold this up. But as these are only experimental coils, they weren't done. Now, as you can see here, where I've done that, you know, I'm probably a bit too close in, but I'll give you an idea. The tape here, which is overlapping, connected here, but just sitting on the carbon on this side, repeats over here, right? This technically here is connect, break, carbon under, tape over with carbon. So it acts as, again, like capacitive coupling, but it's totally shielded. Nothing can get at the coil itself or the coil windings. And this is on both sides of the coil. Normally, these type of coils, if you have a look at some of the commercial coils, they'll have painted cardboard. It will come up over the winding, and there'll be another piece of cardboard there, but it won't connect. It'll be like an overlap situation again, but they only do it here around the winding. So they've got 2 insulated pancakes, but they are connected with a little wire, like down here, like this one here. This wire here will be painted on, a hole poked through, and I don't know why it's not more in the middle. I'm looking for any markings of an old wire. I think there might be one there. Very, 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 very thin hair wire there. Very thin. I think it is. This one's a bit fatter, of course, but that's tinned copper, multi-strand. So it won't give off much in the way of eddy currents in the time domain of the receiver. So we don't have to worry about that. But that's how thin they were using the wires. It's like a human hair. I'll get right in if I can. Somewhere there. And that probably goes through and connects to the other side. I'll flip it round. I'm trying to feel for it. Maybe not. There's a couple of holes here. There's a hole here, a hole there. Maybe a header wire ran from here to here and went through the other side. There's no holes on this side. Or actually, there's a little hole there. May have done, but not critical. As long as you connect this to this with a small wire and then paint over it with carbon so you get a good contact. But you don't want this as a direct short here. It'll act as a shorted winding, even though it is resistive, and it'll kill the sensitivity of your coil. It'll also, you won't be able to measure it because it is minuscule, but it will burn up some of the transmit energy as well. And you know, you're not going to worry about the transmit. There's heaps of grunt there, but you know, you're looking at nanovolt return signals from your targets, and you're going to lose them. You know, they're going to die in the resistance. So you don't want it. The other thing I did find too, that even as a big plate like this, it kills the sensitivity on small targets at depth. So that's why I've broken it into a 4-quadrant overlap capacitive, but still electrically conductive through the middle here, through a very small point in the middle. It's all conductive like so, but it's not a huge mass of conduction. You could improve on this. You could probably make it into 8 quadrants, overlap it with tape, and do the same again. There will be a law of diminishing returns doing that. But if you want, like I say, I haven't done it. Maybe someone out there wants to experiment. So this one, for memory, is a Litzwire coil. I'm pretty sure I used Litzwire on it. It's nice and light. This foam, I don't know if you can see, it's got a scratch on it. And you want to cover these scratches up with new conductive paint, because if you have coils and it has scratches on it like that, you put the coil to the ground and it's going to sound off because it's right where the windings are, and it will interact. The ground will interact with the winding and cause a change in capacitance, and it'll sound off. So some of your coils that go noisy over the years, it's because they are painted with a carbon graphite paint, such as this, and the coil bottom cover sits on this, and through all various mechanical, temperature, whatever, it moves and it just does that and it rubs it away. I found that on a lot of coils, especially the ones that have the painted cardboard type setup, and you'll have areas where it's just like in the middle of the coil on a high spot, it rubs it away, and then you go to use your coil and you know, you ground balance your coil and it won't ground balance properly because you've got ground interaction getting into the structure and upsetting the windings. So that was a very, very good coil. I should actually clean that up and resurrect it. You know, I'd probably take all this off, put some foam in there. You've got to use a low dielectric foam, and what that means is that it doesn't have much absorption. You want to have like, well, this blue foam is a fairly heavy density foam, but it's, you know, you need stability for your coil. You can't use anything like, you know, something solid like PVC or rubber. The dielectric constant's too high. It'll start killing the way your coil operates. It'll kill the Q of the coil, which is basically what we call a quality factor, and it's basically how construction and the layout and all the capacitance, resistance, and surrounding structure affects the coil winding itself. You know, if you make this out of inferior material, the wrong dielectric material, you can actually kill the performance of the coil quite severely. So it's a bit of an art in that. But that is my first very, 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 one of my very first very, very good coils. Now, we moved on from that sort of coil. Now, later on, we got our own vacuum former. We have 2 vacuum formers, and this is one of the coils we vacuum formed. As you can see, we were probably one of the first to use the rubber grommet here, because the cable glands they used to use, the ones you screw up, cut the braid of the cable, and the cable failed. And that was on all the detector coils for many, many years. And I've seen that, the coil went noisy, didn't work, and it broke all the braiding. So, we did that and everyone else followed. So I'll just point that out because this is a very, very old coil. This coil here was absolutely exceptional. As you can see, I had to pull it apart. I had it glued in the housing. And it's busted out the carbon off the foam. This is just one of those white expanded foam materials. It's medium density. It's very small balls. It's not that horrible stuff they use for packing. Some of the packing stuff is very large particle size and just falls apart really easy. This is a little bit different. Still, I've got a better dielectric than the blue stuff, but the blue stuff's used for building. It's for the blue foam they use for insulating refrigerated trucks. And this white stuff here, I don't know if you can see here, it's got a nice finish to it. It's not all balls and fall apart. So it was very, very stable. But this coil here, we used polypropylene wrapped Litz wire, and there is a reason for that, which is reducing wire-to-wire capacitance. It would have been better to use Teflon, but a lot of people, should I say, many people do not know that Teflon, if you bang Teflon against itself or rub it against itself even so slightly, generates electric charge. People don't know that about Teflon. It's what's it called? What's the word? Tribioelectric or something. Anyway, you can look it up on Teflon, and it's self-generating. Just making a charge when you rub it together. So polypropylene has a dielectric constant what is it? 1.8 or 2.2, one or the other, I can't remember. But I've done all this material study years and years ago, and that is the right spacing, wire-to-wire spacing for maximum performance without losing magnetic coupling. So there was a lot of formulas for that. This had tape over here, which was carbon taped on, and as you can see in the end there, that's Litz wire, and that's polypropylene threading, or you want to call it, over the top. That was one of the best coils that we ever made. Now, on this coil here, you can see the very fine wire. I don't know if you can see it there. It's very, very fine, and that earths or grounds. I always interchange those terms. Here to the other side. Now, what I should have done on this coil, and I did not do, I should have done the cut down and the overlap of the masking tape, and had overlap capacitive overlaps over the thing in a 4-quadrant setup. On this one, I didn't do it. The performance of this coil was outstanding, and I'd say if I did an overlap on the coil, it would have been better. I did have a lot of these coils, and then they've all disappeared over the years. I've taken the tape off there so you can just see the winding in there. Now, a lot of this was just done on a horizontal milling machine, and just set up and just make the formers up, cut them, and just push the mill bit in there, and just round you go, and mill it into the depth you want. You know, the other trick with this too, if the windings aren't tight and they can move, like if I actually get this, I can move that like that, that will make noise. It'll sound off. So a lot of the manufacturers started wrapping rubber bands or elastic bands around the coil and holding it together. Not the best material to use. You know, you're probably better off using some sort of expanding low dielectric foam or something. You know, if you have a lot of materials, you can actually get two metal plates, put them up on a capacitance meter and shove material between the plates, and have a look at you know, how much the capacitance increases. And if it increases a hell of a lot, it's a very high dielectric material. You don't want that. You want a low capacitance type material. So you can experiment around and you get stuff like this foam and shove it in, and it's very, very low dielectric. So with a coil like this, you could actually get this foam, and you know, even in strips, you push it in there. You can glue it on. You got to be careful. This stuff melts with most glues. You'd have to use possibly even dabs of epoxy. And if you stabilize it all and had it all compressed so nothing moved, it all dried nicely, then you put your tape over the top, so you got no air gap here. So your tape can't move, you know, if it did this. You know, you don't want your coil doing that because it'll sound off. Lock it all up. There's a bit of fine wire sitting there. There it is, there's a tail. And you'd make a really, really fantastic coil. It would exceed the performance of existing coils that are out there at the moment in the pulse induction detector field. Another thing too, people love doing things to save costs, right? And the thing they don't take into account is the coil cable, right? You know, we say we're doing a construction, we want to lower all the capacitance, so we get a very high Q coil. You can go overboard, but this coil cable, this is one we had made, and it's thicker than most of the others. And the reason being is that it gives a greater spacing from the inner conductor to the outer shield, which lowers capacitance. You start getting a lower capacitance the further away the shield is from the inner conductor. A lot of these coil cables could be 150 picofarads. We've got this cable, I think it's running around about 80 for the same length. So there is performance, makes a faster coil. You can sample in earlier if your detector's capable of doing it. That's why we modify detectors. In a lot of cases, we were doing it with our coils. You've got to be careful what coils you use. So, and the other thing, I do have to mention this, right? And we got the plastic for this cheap. It's black and it's cheap. The lesson is, don't make a black coil unless you live in the Arctic or somewhere, because the black absorbs heat and it gets stinking hot, right? So do not use black plastic, right? Any dark color. Even the early Minelab stuff is green. That will absorb heat greater than a white coil. And over here, come here you. As you can see, when Minelab got away from their dark green coils, they went to white. White reflects the light, which means it will reduce the absorption of, you know, thermal energy from the sun across the spectrum, and it won't get as hot. So white coils are the go. Even the darker grey coils will absorb more heat, like this one here. What you could do if your coils, and I don't suggest you have to do this, but you could get some plastic paint and paint all your coils white. They won't get as hot. Noisy, okay. I know these coils are very low resistance, right? In the windings, they're about half an ohm or so, right? But heat causes thermal noise, right? And minimize all your noise sources. Don't let your coils get hot. The carbon, even in the shield, gets hot, and it can change resistance. It can make noise, right? Like a carbon resistor. Horrible things. Noisy. They're noisy. These detectors are so sensitive, they will be affected by any sort of noise, especially noises that are random and change, can cause interference in the detector. That's an extreme case, I'm saying. I've never actually gone and measured it, but theoretically it is possible. So, the quickest and easiest way to alleviate that possibility is use white coils. Paint them white. Yeah, I did have some other commercial coils here that were pulled apart, and I was going to point out their deficiencies. And then I thought to myself, no, I won't do that. I'll get in the bad books with particular companies because I haven't got all the coils out there, and it would just be like, pointing the bone at one or two manufacturers. I don't want to do that. But what I've pointed out so far, if you take into account how I manufactured those coils, especially the big one, and if you have a look at the way I've done the shielding and the overlap in shielding, it makes for a much better coil. More sensitivity, and would it have less ground effect? Possibly. I have to think about that very carefully. I've actually got to picture it in my head, how it's segmented and if there'd be any interaction. And I don't think so. But then again, I have never got a coil manufactured with the segmentation of the same size, same material, same specification, and one with like a pancake construction. So I haven't done it, so I don't know. I can't do everything. I just haven't got enough time. I wouldn't be able to do anything else. There's just so much to play with and experiment with metal detectors. The whole thing now is that technology is going through another leap of faith, and there's different ways of doing things. I still think that there is still a lot of scope to get a lot more performance out of the standard type of PI, the unipolar type pulse detectors, not the bipolar ones. I think there's a lot more that can be done in the realm of detectors, and even in the PI ones. We can do things like we can put the preamplifiers inside the coils, drive the preamplifier from the back EMF energy of the coil, or even just take part of the transmit pulse. It's going to take a few milliamps. And with the small, tiny, high value capacitors we get now, we can store enough energy, use low dropout regulators, tiny little things, and just have a nice stable voltage supply. And like in some of the VLF detectors, they're putting the preamplifier in the coil, and they're also putting analog to digital converters in the coil. So you could bring your receive signal up in digital format, and it's not going to have any impact by noise. You can demodulate that any which way you want. It's not actually demodulation, it's basically putting it through a D to A, digital to analog converter. Then you can process that whichever way you want. There's a lot of scope there as well. You can put a 24-bit, 2.5 megabit per sample ADC in your coil. You got a stack of data, a heap of data. You can even, you know, the less mass you have in your coil of metallics, the better. You don't want the ground and eddy current return interacting with that metallics of any metal in there. So the layout, the construction's critical, and everything like your metal work and that would have to be like a conductive type. What do you want to call it? Like a crosshatch pattern and stuff like this, where you do have enough ground, but it's not enough to cause interaction with those incoming signals, and also with the transmit pulse too. You don't want that. You're going to possibly get some sort of eddy current delay or something in it. It's going to regenerate a signal. Who knows? But like I say, it's a new frontier with pulse induction, and especially with coils and the signal processing side of it. A lot of stuff, relatively has to stay the same, but there's a lot of stuff that can be done in the actual signal measurement and processing, and getting rid of cable losses by putting some of the tech inside the coil, making things faster, better, lower noise. So they'll go deeper, be more sensitive, and opens up all the gold fields again. Anyway, that's probably enough waffle on this stuff. But what I have done there, I have given out a lot of, what I would call my little trade secrets. But like I say, I'm not going to go in the business of making coils. Someone else can. And if people benefit from better made coils, good on it. It makes it good for the whole hobby as such. So, a few years ago, I did make mention about the big double Ds, how good they were on big gold, and getting rid of some of the hot ground noise directly under the transmit coil winding. And I think I did an article in Gold, Gem and Treasure for that, and I think within 6 months all these big double Ds turned up. So yeah, people do listen, people take notice. You won't get credit for it, but I guarantee you'll see split quadrant shielded detectors turn up. They'll turn up, I guarantee it, right? Someone will start making them and they'll be on the market. But apart from that, I've even got better stuff than that. But that's one layer, okay? There's better than these coils. Like I say, these were done years ago, and I haven't just sat on my bum, done nothing. I've done a lot more research and development on coils, and I've got some absolute doozies, but they probably would be on the cutting edge of being, very sensitive to go and release into the public domain. So for the time being, I'll keep my mouth shut about it. If we're going to make them, we'll make them, and if we don't, we'll tell everyone about it. Anyway, thanks for watching, and go make some coils, have some fun. Catches.